So in today's session, we will be discussing about inner product space. So before that, in the last section, we have stopped in basis and dimension of vectors. So in this slide, you can see I have included the basis and dimension in metric based explanation. So if you are getting a metric, how we can explain basis and dimension. So in metric space, vectors are matrices and the operations are metric addition and scalar multiplication. So you know that we are using two operations here, addition and multiplication. So when we are talking about metrics, the metrics based metric addition and scalar multiplication is used here. So the basis actually have the same definition itself. So it comes under the metric definition, and that's the only about thing here. So a basis of a metric space is a set of matrices that we already know it is linearly independent, and if it spans the entire space, we call it as basis. And the number of matrices in that basis is actually the dimension. So I have two examples here. So the first example is we are taking the space of all 2 by 2 matrices. So you know that 2 by 2 matrices have 2 rows and 2 columns of real numbers. So the entries will be real numbers, which I have wrote there. That is, consider the vector space M 2 by 2 of real numbers. That is, the matrix will be on the form ABCD, and ABCD belongs to R. So you know that the basis will be 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0. So you get whether this is a basis, like the four matrices are linearly independent and also it spans. By using this 4, we can make any other matrices in the form 2 by 2. So these matrices are linearly independent and span all 2 by 2 matrices. So hence the dimension is 4. So any matrix in the space can be written uniquely as a linear combination of these basic matrices. So the other example, when you look the second example, you will get it clearly. So the subspace of symmetric matrices. Okay, so I'm taking subspace of symmetric matrices of 2 by 2 matrices. Okay, so consider the space. The symmetric matrix means A transpose will be equal to A itself. So here the matrix look like A, B, B, C. Okay, so where A, B, C belong to R. So here you can see the second entry and the third entry are actually B, B, right? So the three things we want there is 1 0 0 0 0 1 1 0 and 0 0 0. With this three matrices we can make other matrices in the form A, B, B, C. Okay, so if we are adding also, we get the same matrix. So actually it's a vector space. You can check whether it is a vector space or not by using the 10 axiom. So here with this three matrices, we can actually span, or we can make other matrices of the form like these are of the form of S. So these matrices are actually linearly independent and span all symmetric 2 by 2 matrices. So here you can see the dimension is 3. Okay. So by we no need 4 matrices there, we need only 3 matrices in the form 1 0 0 0 0 1 1 0 0 0 0 1. Okay. So I understand how we can define basis and dimension in matrix based explanation. Okay. So the next thing we have to learn is about inner product, orthogonality and projection. Okay, so the first one is inner product. So inner product is actually it's actually a function, like we can define by using the following condition. So an inner product is a mathematical operation that generalizes the dot product and allows us to define length, angle and orthogonality in vector space. So if you are taking a vector space V, it is actually operation and the product is a function. So you can see two dot there, right? So two dot represents two vectors actually. So it is from V cross V to R. Okay, so it is from V cross V to real numbers. We are mapping V cross V to a real number. That is actually this operation is done by. So that satisfies the following properties. So there are three properties a inner product should satisfy. The first one is symmetric. That is, inner product UV is equal to inner product of VU. The second one is linearity in the first argument. Okay, first argument means the first object. If we say object, the first thing, that is, if UV is the inner product, U is the first argument there. So here you can see that the first argument in the second point is Cu plus V comma W, right? So it is actually, it follows linearity in the first argument. Okay, so we can write that as C into U plus inner product UW plus VW. And the third one is positive definite, that is UV, that is inner product UU is always greater than or equal to 0. So if it is equal to 0, then U will be equal to 0. And also this is actually if and only if condition, that is UU equal to 0 if and only U equal to 0. So these are the three conditions you should learn about inner product. Just understand what is inner product. Okay. So the standard inner product is actually the dot product that we know. You know, if we take two matrix, two vectors U and V, and if we find the dot product, it is actually U1 V1 plus U2 V2 plus U up to UN Vn, right? So similarly, the standard inner product we are using here is actually the dot product, that is inner product UV is equal to U1 V1 plus U2 V2 plus up to UN Vn. So I have provided an example there. So you have two vectors U and V. U is 1, 2, 3 and V is 4, minus 1, 2. So the inner product is actually 1 into 4. That is, we are multiplying the corresponding product, entries. That is 1 into 4 plus 2 into minus 1 plus 3 into 2, which is equal to 4 minus 2 plus 6, and you got the answer 8. So it is actually mapped to a real number, right? 8 is a real number. So this inner product UV is mapped to 8. So hope you understand that. Just understand the definition and just understand this example. We are using this definition to find the inner product. So just know that inner product UV is U1 V1 plus U2 V2 up to UN Vn. So the next one is norm of a vector. Okay, norm of a vector is denoted by the symbol. You can see there. The norm is actually the length. Okay, the norm is actually length of a vector U. Is defined using the inner product. So the norm is actually root of inner product UV. Okay, so here I have an example. If we are getting U 1, 2, 3, the norm is actually root of 1 square, root of norm of UU, right? So UU is 1, 2, 3. So we are multiplying the corresponding numbers. So 1 into 1, that is 1 square, 2 into 2, that is 2 square, 3 into 3, that is 3 square. So you will get root 14. So this is actually the norm of the vector 1, 2, 3. And the third one is orthogonality. So if you are getting two vectors, how can you say whether that two are orthogonal? So that the thing is, inner product, if the inner product UV equal to 0, then we can say two vectors are orthogonal. So it's actually is meant that UV is actually perpendicular. Okay. So orthogonality represents perpendicularity in geometry and independence in computation. Okay. So if you want to show whether UV are independent, we will show it is orthogonal or not. So you have an example there. If I am taking U and V, if I am taking U and V, so UV is 1, 2, minus 1 and V is 2, minus 1, 0. So I have to check whether this two are orthogonal or not. So I am taking the inner product of it UV. So it is actually 1 into 2 plus 2 into minus 1 plus minus 1 into 0, right? So 2 minus 2 plus 0, you get the answer as 0. So we can say that U and V are orthogonal. So just remember the things. Okay, so what is the inner product? We are using the standard inner product, that is we are using the definition of dot product. And the second thing you learned is norm of the vector, and that is actually root of inner product UU. And third one is orthogonality, that is if you are finding the inner product two vectors and if you are getting 0, then we can say it is orthogonal or two vectors are perpendicular. That is the meaning of that. And the fourth one is orthogonal, and I am discussing here what is orthonormal set. Okay, so you already know what is orthogonal set. Consists of non-zero vectors that are pairwise orthogonal. So I am considering a vector space, not vector space, I am considering a set with vectors, that is u1, u2 up to un. So it is an orthogonal set if it is pairwise orthogonal. That is, if I am taking inner product of u1, u2 and I am getting 0. So next I am taking u2, u3 and I am getting 0. u3, u4 and also u1 with every vector. Okay, u1 with u2, u1 with u3, u1 with u4. I am taking each pair and I am getting that is orthogonal. That is the inner product of that is 0. Then we will call it as orthogonal set. And when you call a orthonormal set, that is, if the length of the vector is actually 1. Okay, so that is you know to find the norm, right? So the norm should be 1. The length should be 1. So here I have overall definition of that. That is inner product ui uj equal to 1 when I equal to j and 0 when I not equal to j. So ui. So if I am taking u1, the length inner product should be 1. And if I am taking different members, okay, u1, u2 or u1, u3, I am taking different members and finding the inner product. Then if I am getting 0, then it is orthogonal. So these are the combined definition of that. That is ui uj equal to 1 if I equal to j. If I am taking the same vector, I will get the inner product as 1. If I am taking the different vector and if I am getting it 0, then we will call it as a orthonormal set. Okay. So orthonormal means it should be both orthogonal set and also the vector should have a unit length. Okay, so just remember that. And the fifth one is projection of a vector. So it is very important. That definition is very important. We are using it in our coming sections. So you should study the definition of the projection. So actually, what is a projection? Projection of a vector v onto another vector u represents the component of v in the direction of u. Okay, so we are taking a vector v and the projection of the vector v, and I am taking another vector u represents the component of v in the direction of u. Okay, so represents the component of v in the direction. So the direction will be of u and the component of v in the direction of u. Okay, so the projection formula, you should study the formula. It's very important. It is actually projection of v. So it is similar to the definition of projection you have learned in 5th or 11th standard, right? So we learned it in the form of in a cross product and dot product, I think. So here we are learning it by using the definition of inner product. So projection u of v. Okay, so we are using the direction u. We are using the component of v. That is actually projection u of v is actually the inner product vu divided by inner product uu into vector u. So that is actually the projection. So you should learn that definition. You should learn the formula. It is very important. Here I have an example for projection. I am getting two vectors u equal to 1 1 and v equal to 2 3. So I am computing. First I should for finding the projection I should need inner product vu, inner product uu, right? So I am finding that inner product vu, you know how to find that. That is 2 into 1 plus 3 into 1 equal to 5. And in the product u is 1 square plus 1 square, that is 2. So I am applying the formula, that is 5 divided by 2 into vector u, right? So vector u is 1 1. So you get the vector 5 by 2, 5 by 2. So that is actually the projection of the vector v onto u. Okay, so hope you understand what is projection. So the formula is very important. You should study the formula. We are using that in our coming sections. Okay, thank you all. Let us stop this section here.